Welcome to this deep dive. You are about to learn why, painting a nuclear reactor is basically a life or death science experiment. We're running through 7 brutal questions from the AMPP nuclear exam. And I mean, by the end of this, you'll see why just a single peeling paint chip could literally cause a national emergency.
Yeah, what's really fascinating here is just how absolute the standards must be. So to truly absorb this complex material and, help you master it, we're going to proceed at a deliberate, measured, and slightly slower professional pace.
Exactly. We've got exactly 7 critical practice questions to cover to really understand the safety and compliance standards of nuclear coding operations. So let's just jump right in. Question 1. In the context of coding service level classifications, which scenario strictly mandates the use of a design basis accident qualified coding system?
The correct answer is A. A design basis accident qualified coding system is required when coding failure could affect safety-related equipment or post-accident recovery functions. In primary containment, failed coding debris may detach during an accident and be transported to sump screens, strainers, or emergency core cooling system components. Because this could impair the emergency core cooling system, this scenario strictly requires a DBA-qualified coding system.
Okay, wait, let me just translate that for a second. If the wrong paint chips off, it essentially turns into, like, plaque in the reactor's arteries.
Yes, exactly.
It just clogs the water filters right when the reactor desperately needs to cool down. So if the stakes are that high, how do we even test the paint? Well, question 2. When evaluating a coding system for design basis accident qualification, the testing parameters must simulate which of the following specific operational extremes?
The correct answer is B. DBA qualification testing must represent the severe conditions expected during a design basis accident. These conditions typically include high temperature, elevated pressure, radiation exposure, and sometimes chemical spray or immersion, depending on the plant scenario. The purpose is to prove that the coating can remain intact and not generate harmful debris under accident conditions.
Wow. I mean, you're blasting it with pressure, chemicals, and radiation.
Oh, absolutely, yeah.
But wait, lab tests are one thing, Like, I could have the toughest paint in the world, but if the applicator does a terrible job, it still fails, right?
Yeah.
It's like a mandatory safety checkpoint. Question 3. During the execution of a coding project in a nuclear facility, what is the primary operational characteristic of a designated hold point?
The correct answer is C. A hold point is a mandatory stop in the work process. Work cannot continue until a qualified inspector or authorized representative verifies that the required step meets the specification and gives formal approval to proceed. In nuclear coding work, hold points are important because later steps may cover or permanently affect earlier work, such as surface preparation quality, cleanliness, primer application, or dry film thickness.
Right. Makes total sense. It's like pouring a concrete foundation. If you don't inspect the rebar before pouring, you just can't go back once it's buried.
Precisely.
Now let's zoom out a bit to the area around the painters. Dropping a wrench into a reactor pool has to be disastrous. Question 4. What is the primary objective of implementing stringent foreign materials exclusion controls during surface preparation and coating activities near the spent fuel pool?
The correct answer is D. Foreign materials exclusion controls are used to prevent unapproved materials, debris, tools, abrasive media, or loose items from entering sensitive nuclear areas. Near the spent fuel pool, foreign material could damage fuel assemblies, interfere with equipment, or create retrieval and contamination problems. Therefore, the main objective is to protect nuclear fuel integrity and system functionality.
So a drop scraper could literally damage the nuclear fuel itself. Yikes.
Yeah, it really could.
But here's what I don't get. Who actually enforces this? Like, if federal regulators aren't the ones on the ground holding the clipboard, how do they prevent a disaster? Question 5. Regarding regulatory compliance in nuclear coding operations, what is the primary function of the federal nuclear regulatory guidelines?
The correct answer is A. Federal nuclear regulatory guidelines establish the safety expectations, legal requirements, and compliance framework that nuclear facility licensees must follow. They define the regulatory basis for safe operation, quality assurance, and protection of safety-related systems. They do not directly formulate coatings, supervise all inspectors, or manufacture inspection instruments.
Ah, okay. So they build the legal scaffolding, but the facility itself does the heavy lifting.
Right, exactly.
Now, let's talk about the invisible forces those guidelines account for. I mean, I always assumed radiation just sort of like burns surfaces, but it's way more insidious. Question 6. How does prolonged exposure to ionizing radiation typically compromise the structural integrity of polymeric coating systems in a nuclear environment?
The correct answer is B. Ionizing radiation can degrade polymeric coatings by breaking polymer chains, known as chain scission, and by creating additional bonds between chains, known as cross-linking. These changes can cause embrittlement, cracking, reduced flexibility, and loss of adhesion. In a nuclear environment, radiation resistance is therefore a key factor in coating qualification and long-term performance.
Wow, okay. So radiation basically plays microscopic scissors and glue with the molecules,
That's a great way to put it.
just cutting chains and forcing weird, brittle new bonds.
That actually brings us to the cleanup. If you're scraping off this irradiated, chemical-laden paint, where does it even go? Question 7. During surface preparation in a radiologically controlled area, the generated abrasive blasting debris is classified as mixed waste when it contains which combination of elements? The correct answer is C. Abrasive blasting debris is classified as mixed waste when it contains both radioactive contamination and chemically hazardous constituents. For example, debris may be radioactive because it was generated in a radiologically controlled area, and it may also be hazardous because it contains heavy metals, toxic coating residues, solvents, or other regulated chemical components. This combination makes it mixed waste.
Man, so it's a double threat of radiation and chemicals.
You have just mastered 7 critical pillars of nuclear coating standards, spanning DBA qualifications, hold points, radiation degradation, and mixed waste.